Okay, we're going to be doing a quick lesson on complex numbers. The focus of this lesson will be just to derive the complex numbers so that we can see their applications towards roots and regarding polynomials. So when talking about complex numbers, commonly it's introduced examining the following equation. And if we were to be looking to solve this equation, finding real values, you'll see here that no real values exist. You'll see if I want to solve this equation, there are no real numbers that you can square that it's going to give you a -1. So therefore, there is no real solution to this equation. At this point, what is done, we're going to introduce a number that satisfies this equation. I'm going to let I be a solution to the equation x squared equals -1. So therefore, we have the property that I squared is equal to -1. And we call I an imaginary number. So this is kind of the where complex numbers began, is we were taking a look at this equation, which has no real values that satisfy it. We're letting I be such a number that satisfies this equation. This number is not a real number because no real number exists. It's an imaginary number, and it has the property that I squared equals -1. So now we've got a complex number denoted with I that satisfies the equation I squared equals -1. From here, several results follow. So the first thing we know is we have I squared equaling -1, or equivalently, I is equal to the root of -1. And these are both common ways of representing or discussing your complex numbers. One thing to watch out for here is we know -1 is equal to I squared, which is going to equal I times I, which is equal to the root of -1 times the root of -1 of -1 times -1, which is the root of 1, which is 1. So as I went through this here, there's obviously a problem because we know that -1 is not equal to 1. And the question becomes is where did the mistake occur? And with this relationship here, we've got, again, -1 is not equal to 1. There's a problem here. Where did this issue happen? Right here. And this is one risk when you write your I value as the root of -1. Just be careful when you're working with these roots. Not all the properties follow through. One property that does not follow through from the real number system is when you look at square roots. I cannot apply my exponential properties as I did here, putting these together, unless the function itself is defined. And you know that the root of -1 is undefined, so your exponential properties fail at this point. And that's how we ended up proving that -1 is equal to 1. We applied our exponential properties here. So just be mindful when you're working with your complex numbers. Okay, so we've just defined a complex number. Let's take a look at defining the complex number set now. Your complex numbers are denoted as follows, and what it is, it's the collection of all a plus bi, such that a and b are any real number. You'll notice here that if we let b equal 0 in this equation, if we let b equal 0, effectively you get rid of the complex portion. You're just left with your real portion. So your complex number set is equal to the real numbers. So your real numbers are actually contained inside of your set of complex numbers. And again, that's because if you do let b equal 0, there is no complex portion, only a real portion, so it is a subset. Just some quick examples of values in your complex numbers. Again, this is true for any real number that you choose. I could let a equal 1/2. I could let b equal the root of 2 and then tack on an I, and that would be a complex number. I could look at pi plus 2i. I could look at a can be 0. This would be 0 plus 4i. And again, you could have 1/2 minus I as well. These are all examples of complex numbers. All right, for any real number a and real number b, sub it into your a plus bi expression, and you've got yourself a complex number. So now we have a larger set than the real number system. That's the complex numbers. Now let's take a look at how do the complex numbers relate to polynomials and their roots. So it turns out that polynomial roots come in pairs. So what that means is that if in this case here, if a plus bi is a root of our polynomial, so if you have a complex number that is a root of your polynomial, then its complex conjugate, also known as a minus bi, is also a root. So we have the property that complex roots come in pairs. So given a polynomial, it has complex roots. Those roots would be 0 complex roots, 2, 4, 6, 8, etc., depending on the degree of the polynomial. Let's take a look at some examples to kind of illustrate some application questions of this now that we know that complex roots come in pairs. So for the following example here, this is a degree 4 polynomial, and therefore I know this has 4 roots. They could be all real, all complex, or a combination of those, but I know the following in terms of the possible decompositions of its root system. Either I can have all real numbers, so 4 real, or if I were to assume I have 3 real, I would then have to have 1 complex number. And as we know now, that because complex roots come in pairs, that's impossible. You can't have that decomposition. So therefore, another option here is I could have 2 real numbers and 2 complex numbers. And lastly, I could have 4 complex numbers. So the possible decompositions here of this polynomial degree 4, either it's all real numbers, 2 real, 2 complex numbers, or all complex numbers, and that's it. So now that we know complex roots come in pairs, you do have this. Let's take a look at another example of this. So for this degree 10 polynomial, I know it has 10 roots. Those roots can be all real. You can have 2 complex, 8 real. You can have 4 complex, 6 real. You can have 6 complex, 4 real. You can have 8 complex, 2 real, and lastly, you can have all complex numbers. So this polynomial degree 10, its root decomposition will be one of these 1, 2, 3, 4, 5, 6 different options. Those are the only possibilities that you have in terms of this root system. We'll never be in a situation where you have like 9 real roots and 1 complex root. And let's take a look at this example here. This is a polynomial of degree 3. So again, I know it has 3 roots. So either they can be all real roots, they can be 2 complex roots and 1 real root, and that is it. So those are the only possible 2 combinations that we have for this situation here. You'll notice quickly we can actually see what type of decomposition we have here. If I do synthetic division on this at 1, you're going to get here, going through synthetic division, again, we're always adding. It's going to give me 3, 3, 3, and 4, so that's no good. Try -1 here. Again, using the rational root test, that's the only 2 options if it does have a rational root. And it actually does come out to be a root at -1, so this will decompose into x plus 1 times x squared plus x minus 1. And quickly here you can see if I use my quadratic equation, this quadratic will yield the following roots. And in this example here, we have a root at -1 and then 2 irrational roots at -1 plus or minus root 5 over 2. So this polynomial ended up having decomposition of all real roots. 2 were irrational and 1 was a rational root. All right, let's take a look at some examples of working with complex numbers. So when working with complex numbers, we want to be able to solve these sorts of equations, finding our complex roots. So to start us off here, if I have something like x squared equals -3, I know that x squared could be rewritten as x squared equals 3i squared. I can then take my square root, so it's plus or minus, and you end up getting plus or minus the root of 3i. So in this example here, x squared equals -3 has 2 solutions. One is positive root 3i and the other is negative root 3i. Notice if I were to sub this into the equation, it does satisfy it. Just to show you, going to this equation, if I sub in a root 3i and I square that term, you're going to end up getting here, you square the root 3 and you square that I. The square of root 3 is 3, and I squared is -1, giving you your -3. Likewise, if you sub in a minus root 3i, you'll also see it does satisfy the equation. If I'm looking to answer question 2, we can change that negative sign to a 4i squared. Then taking our square root, we're going to get the square root of 4i squared. Again, that's plus or minus, which gives us x equaling plus or minus 2i. And these are the two roots, complex roots of this equation. Doing the same thing for x squared equals minus 36. This is going to be x squared equals 36i squared. And therefore x is the square root of 36i squared, which means x is 6 plus or minus 6i this time. And these are all roots to these equations, complex roots. All right, let's take a look at this one here. For this one here, again, you want to solve this equation. If you calculate your discriminant on this, it's going to be b squared minus 4ac, and you'll see your discriminant is -3. It's less than 0, so we would say at this point it has no real roots. But now we can go further with this. If I go to use my quadratic equation, you're going to get -1 plus or minus the root of -3 this time over 2 times 1. So this becomes -1 plus the root of -3 over 2. We can now push this a bit further. I know that this is going to end up being -1 plus or minus the root of 3 times the root of -1, right, over 2. So this becomes -1 plus or minus root 3i over 2. And we end up getting complex roots here. So you'll see this degree 2 polynomial has 2 roots, and they're both complex roots. All right, that concludes today's lesson on complex numbers. Again, this is a brief introduction, but now we can make a connection between the roots of our polynomials, including their complex roots should they exist. Thank you.